Okay, so we're going to solve this problem. We're going to find the internal shear and bending moment as a function of x. Now, we've talked about this before, so this problem is going to be a little different than the past because we have, over the first 12 feet, a continuous loading function. So we should therefore be able to write a set of shear force and bending moment equations for that. That would be good from x equals 0 to x equals 12. They would not be valid from 12 to 20. Then I would make a second set of equations that would be valid from 12 to 20. So when you see me write that notation down, I'm just telling you that that set of equations is just good for a certain range, and another set's good for additional range. Now, at the point where they join, say x equals 12, there should be some what? Continuity. The shear and the moment probably will be the same from both of those equations. So you will get a chance to kind of check that. Also, before we get started, what do you think the shear force and bending moment at B is?
0.
Well, the bending moment is 0, but see with that applied load right there at the tip? It's a little bit tricky. There's going to be a shear there, and it's going to be equal to 20. But we know what it is. What about over here at this reaction? Well, you could find the reaction so you know what the bending moment and the shear force were to start. So let's proceed with that strategy. So I'll find my reactions, I'll make some cuts, and we'll go from there. I think I want to do something a little different this time, just to show you the possibilities. So if I make a cut somewhere in that structure, you want to work the left side or the right side? For me, I think the choice is clear. Look at this right-hand side. There's a lot to keep track of, right? If this were x, what would this distance here be? 12 minus x. And then, of course, this is an additional 8 feet. So there's a lot of things to keep track of here. So I still think for the equation for this first 12 feet, I'm going to go with the right-hand side. I'm sorry, the left-hand side. And then we'll come back and talk about this one in a minute. So in order to do this, I'm going to need the reactions. So let's quickly draw the free body diagram for this structure. I've got this 20 kip force here on the end. I'm going to do a concentrated equivalent of this. So it's a rectangle,
48.
Base times height, 48. And it's going to be right in the middle, which from point A would be 6 feet. And of course, this distance would be a remaining, what would that be, 14 feet?
Yeah.
And then I'm going to come over here on the reaction at point A, and I'm going to assume positive shear at A and positive bending moment.
Why do you assume that?
I always assume positive shear force and bending moment. That's what I do. That's what I suggest you do. Because when your equation gives you a negative value, then what do you have? Negative shear force and negative bending moment. So you don't have to go back and rectify your sign with what your assumptions are. It's kind of analogous to always assuming tension in a truss. And if you get a negative, well then it's just compression. I can tell you that the moment's going to be negative, but I still assume positive. So let's go ahead and run the equations real quick. So if I sum moments at A, so I'm going back to static, so I use right-hand rule for my moments. Make sure it's in equilibrium. What do I have? With right-hand rule, what kind of moment is this? It's negative. This 48 kip creates negative moment. And it'll be 48 times 6 feet. And this 20 kip creates negative moment. And it has a moment arm of 20. So when I solve for my moment at A, I get a negative. I have no idea what that's going to be. Somebody help me out with that.
688.
688 kip feet? Is it point something or no?
Nope.
So that kind of matches my intuition. And then I'll go ahead and sum forces quickly in the y direction. and I should find my shear force. My shear force is acting up, and these two forces are acting down. So it looks like the shear at A is equal to 68 kips. So I know where my equations are going to start. So with that said, I'm going to look at this first body. So this set of equations is going to be good from 0 to 12. Now why is it good from 0 to 12? Because that's the range of my load from 0 to 12. When it goes past 12, I have to start again. So this free body that I'm getting ready to draw is going to be good from 0 to 12. So right now that's a distance x. My reaction on the end is I have a shear force acting up of 68 kips, and I have a negative bending moment of 688 feet. And then I'm going to come and assume that I have positive shear and positive bending moment, which are the things I want to find. Also, I'm going to get a concentrated equivalent for my force. What's it going to be? What's a rectangle? So this is going to be base x times height 4. This is going to be 4x. And what's the distance from the cut? The base divided by 2. The base is x, so that's going to be x divided by 2. Everybody see that? So all I have to do now is apply my equilibrium equations. So I'll come over here and I'll sum moments at the cut and make sure it's equal to 0. So that will be, starting on the right hand side, that's my moment, which is positive. This force of 4x is creating positive moment about the cut with a moment arm of x over 2. Then I've got this 68 kip creating negative moment with the moment arm of x. And then this 688 is positive. Sorry, I kind of ran out of room there. Apologize for that. I left my units off, but I'll straighten it all out now. So when I solve for the moment as a function of x, what do I get? Looks like I get minus x squared, minus 2, let me start that again, minus 2x squared plus 68x minus 688. And all of those should have units of kip feet. So when x is equal to 0, what's my moment? Negative 688, right? And that matches what I found here. So that seems to be working so far. Can I check it anywhere else? I know the moment is 0 out here at B. Can I plug in x equal 20 in this equation? No. Can't do it. So now I'll sum forces in the y direction, set that equal to 0. Let's see what I get. So I get the shear force is down, my 4x force is down, and 68 is up. So I'll solve for shear, and it looks like I get minus 4x plus 68, and that will be kips. Do I have some place where I can check my shear? Yeah, at A. The shear should be 68. So at A, that's x equals 0. Looks like that works too. So at least I've captured the 2 points that I know. Also, is the derivative of the moment equal to the shear? Looks like it is, so I'll put a little check mark there. So far it looks pretty good for me. I have a relationship I like, and it matches the 2 points I know. I don't know what's happening over here at 12 yet, but maybe I'll come back and check that later. So what do? Am I finished? No. I need to come over here and now go from 12 to 20. So I'll make a cut somewhere here. Now, a little hard to see. You want to work the left side or the right side?
Right side.
Right side. So I'm going to redraw that so it'll be a little easier to see. Lots of advantages here. Just looking at the right-hand side, I don't care what the reactions are. So if I had made a mistake with the reactions, they're not going to filter into this equation. Plus, I only have one thing to keep track of. So now, if I look at an equation that's good from x equal 12 to 20, I kind of like to draw it this way. So there's my little stub of my beam with my 20 kip force. So over here from the left, that's still the distance x to the cut. So what's the little stub of the beam left over? What's its length? 20 minus x. Right? Everybody see that? It's got really quiet in here. You guys following this?
I don't see the 20 minus x.
Well, how long is the whole beam?
The whole beam is 20.
So if I go to x to the middle, how much is left? X plus 20 minus x should equal 20. And it does. You see that?
Okay, because I was looking at the little x behind our cut.
This is a new little x.
Okay.
This is a little x between 12 and 20.
Okay.
So it's operating out here. Actually, it would be the same in here too, except remember this one only went to 12, because that was the range of that first one. Is that working? Okay, so I have positive shear at the cut and positive bending moment at the cut. So let's find those. So if I sum moments, I'm using right-hand rule for my sign convention at the cut. What kind of moment is this? Positive or negative?
That's a negative.
That's a negative moment. What's the moment about the cut create for this 20 kip? What kind of moment does it create about the cut? Positive or negative? Negative. And what's its moment arm? 20 minus x. So I'm going to solve for the moment. It's going to tell me the moment there is minus 20 times 20 minus x, and that'll be kip feet. You don't have to expand that if you don't want to. Now I do know something about the moment between 12 and 20. What do I know? I know the moment to free end. What's the moment to free end? It should be 0. That's at x equal 20. When I put in x equal 20, what do I get? I get 0. So that seems to work. Let's go ahead and do my sum the forces in the y direction. What do I get? Well, shear is acting up and 20 is acting down. So it looks like my shear is a constant equal to 20 kips. Is that a constant shear right there at the end?
Yes.
Let me show you something. If I let me pick a different color just for fun. If I look at that little blob right there, and I'm going to make a really little thin slice. I'll even call it dx. So on the far right side is my applied 20 kip force, and then internally this is my positive shear. Well, that little blob, even as small as that, has to be in equilibrium. So if I sum forces in the y direction, what do I get? I get shear is up, 20 is down, the shear is equal to 20. So it says that I do, in effect, have positive shear just at that point. And that matches with what my equation says. Yes?
If you were solving for x equals 12, which set of equations would you use?
Both. That's a very good question. Let's do that. What happens at x equal 12? Well, let's do the moment first. So let me call this 1 and 2 and 1 and 2. So what is the moment 1 at x equal 12? Somebody compute that. And then what's the moment from 2 at x equal to 12? This is pretty easy. I can do that one. That's 8 times that. So it looks like it's negative 160. Put in 12 up there. What do you get? I bet you get negative 160.
Yes.
So you can see that the moment is continuous at that point. Now, if oddly enough, right at 12, I had an applied moment, then these two values would differ by exactly that applied moment. But we don't have one of those. What about the shear there? What's the shear from 1 at x equal 12? And the shear from 2 at x equal 12? Well, I can get the second one. That's easy. It's 20 kips. What's the shear from this one at x equal 12? Looks like 20 kips. So you can see they are continuous. And there's really not a point load there to make it jump. So that's another way you can check those things. You can actually look to see if your equations give you what's actually happening.
So if you did have an applied moment at 12, you wouldn't ask for the moment, the bending moment at 12. Because there would be two different answers, correct?
I'm not quite sure what you said, but we do get the same bending moment no matter what equation we use.
Unless you had an applied moment.
Unless you had an applied moment. So you'd have the moment from this side would be just to the left of that applied moment, and the one on this side would be just to the right. Remember how we did the shear under a force? The change in moment would have the same thing under an applied moment. Applied moments are rarer things in structural mechanics than an applied force. So where's the maximum moment? It's a cantilever. So it should be at the cantilever. And that would be, which equation do I use for that? This one. And where would I evaluate it? X equals 0. X equals 0, it's minus 688. Where's the maximum shear? At A. Which equation do I use? This one? No. This one. And I'd evaluate the shear at x equal 0. So it should be 68. Isn't this beautiful? Isn't it amazing how this comes together and works? Any other questions about this one?